So the first thing I was going to do is ask the question, but I guess that's out. But I don't know how much you've been involved with high performance buildings and so on, but I do a lot of work in codes and standards and trying to move things forward. And we have to go to high performance buildings whether we like it or not. The problem we run into is everybody has a different definitions of what that means. But and we're expanding it. We're now getting into greenhouse gas emissions and a whole bunch of other stuff. So I'm going to sort of focus on the learning objectives. And my passion is the building envelope. So I'm not going to get into anything electrical or anything mechanical equipment. It's just going to be based on the building envelope. So, and I travel. I just came back from a week meeting in Stockholm dealing with international standards. And there's a movement not just in North America, but around the world to do a better job, to have buildings use less energy, perform better, be more resilient, all those type of things. And as I've looked over the years I've been involved with the industries, a lot of times if there's a new program comes out by the government or a utility, they focus on the really easy things. So we start to change light bulbs and so on. And then maybe we change the heating system or something. Sort of the message I'm trying to get across in this presentation is we've got to start with the building envelope. Because this building isn't designed for 1 year, 5 years, 10 years. This building that we're in here today should be standing and very usable in 100 years, 150 years, and so on. So that's the point I'm trying to get across is we not only need them high performance as far as using less energy, producing less greenhouse gas emissions, everything, but to be durable for decades, if not centuries. And we've done a good job of going from building energy inefficient buildings to more efficient buildings. But if we take a look at the code, we're no longer going to save 20 or 30% by doing a single thing. We're going to be using small increments. Well, those small increments are very, very important to get to our goal that we want. And part of it, I'm saying to members of Metalcon and to any trade associations, the government can do so much, industry can do so much, but the associations brings people together like you see today. It's people are at this conference because they have like sort of ideas and ways to go. And we need to have more of that interaction as an association. And as I mentioned, carbon is becoming a big thing. Over the last year, it was hardly mentioned, and over the last year, now we have an ASHRAE standard. There's standards coming out in the ASTM, starting to get into building codes. When I talk to architects and design professionals, they want all the answers, what's your EPDM, all these type of questions. So that's really gaining traction. So I'm borrowing this from a state up in the Northwest. They took a look and they made their own codes of where they want to get and how quickly. And I liked it because right after basic building design, we got to design them properly. We get into the enclosure, the building envelope itself. And once you get that done, then you work on the mechanical system and then you deal with on-site. There's also another term that's very used all over the place is net zero or nearly net zero and so on. And everybody has a different opinion, but the idea is that you build your building envelope so good, you put very efficient mechanical equipment, lighting and so on, that the balance could be supplemented by on-site energy production. This could be solar, this could be wind, this could be a whole bunch of other different things. So I've thought it was a really good way of understanding what we have to do to get to where we want to go. And as we look at the building envelope on it, you see the critical barriers. Well, one of the things that a cladding system does is it really sheds 99% of the water. And then once we get past the bulk water, keeping that away from buildings, then we go into a secondary defense. That 1% that gets past the cladding system still needs to be stopped, and we have a water-resistant barrier. We need thermal insulation, and then we have air barrier, and of course that's the main thing that we focus in. And sometimes we need a vapor barrier or vapor retarder, depending. And that's one of the most misunderstood control layers that we have in our whole building. So as we looked at the enclosure as we go forward, they looked at insulation. We need high levels of insulation. We're going to go up to somewhere between R30 and R40 insulation. Airtightness becomes really critical, and we're seeing that grow right across the United States with more jurisdictions requiring it in the code, but even more importantly, more buildings, the building owner or the building professional, the engineer, the architect, whoever it is requiring very airtight buildings for a bunch of reasons. And then we need to optimize our glazing. In some areas of the United States, heating, interior heating is a big issue. And so although we have very highly insulated to keep the heat out, we have to optimize in our glazing on there too. And so why do we, and of course we're the Air Barrier Association of America, so we sort of focus on the air tightness. And why do we want to do that? Well, this is from the U.S. Department of Energy. They're taking a look at all the places where we use energy in the United States, and roughly a third of it is buildings. Now, we got transportation and we got industrial uses. And transportation, we're going to have more and more cars. We're moving to electric cars. We're seeing more electric-driven cars. Most manufacturers bring them out. So that's going to help reduce some types of energy, but we still got to produce electricity. In industry, we don't want them to use electricity. We want them, or energy, we want them to use it more efficient, produce more gadgets, whatever it is, for the same amount of energy, because we got to grow, both as a nation. And then so one of the places we can do something is the 40% that's used in buildings. And if you take a look at the heating and cooling in both residential and commercial, it's about the same. So as the Department of Energy looks at this, they understand that this is a good place that we could start. Not just a new construction, but also going back and renovating the existing buildings. And if this is point out, you got a whole bunch of BTUs, you got a whole, they call it 1.2 quads. That's a whole lot of energy if we just built all our buildings really airtight, tremendous amount. That would allow us to use all that electricity or energy that we're using to heat our buildings, be used for either transportation or for making things. And this is in their multi-year program. They wanted to know where you lose the energy in buildings. You see again commercial and residential, and if this is the line that you want to look at. So compared to windows and walls and so on, you got the highest number of highest potential for energy saving just by making our buildings airtight. Now, one of the things that you got to keep in mind is a lot of the materials you need for an air barrier is you're already using on a building. Metal, as an example, all the metal fabrication you see around here, metal is a perfect air barrier. So you already have the big parts of a building. If you want to use metal panels to be an air barrier system, you got to just do with the details, and we're going to go into that. So what does the building do? It determines how much heat needs to be added, subtracted, and how much moisture needs to be added, subtracted. We have a level of comfort, both in temperature and relative humidity, that we feel nice. We don't want to be outside today because it's too hot. In the wintertime, we don't want to be outside, or we could have too much humidity. We like to be really, really in this very narrow band there. So how do we look at minimizing heating? As I mentioned earlier, let's start with the main thing, which is the building that separates the inside from the outside, or one environment from another environment. And you can do it different ways. You can have a perfectly balanced mechanical system and a building envelope, so they're about even. You can also do very little on the building envelope side, so it means that you have to have really good mechanical equipment. Or if you do it the other way around, let's do a really good job in the building envelope, and then we don't need much mechanical equipment. A good friend of mine is a masonry contractor. He lived in a 1940 house, story and a half house, really badly built as far as energy, insulation, and so on. And his son got a scholarship, and for his thesis as an architect, he built a structural masonry house, 10,000 square feet. His other house was just over 1,000 square feet. New house was 10,000 square feet, and built with lots of insulation, super airtight and so on, and his energy bills were the same, just to show you how much we can do there. So we can always make up a bad building envelope, as I say, by putting better mechanical equipment in, but that's not the right way to go. That's wasting energy, wasting your money, and so on. So what we want to do is we want to find our optimum R value for insulation, so that we don't have to put excessive size of mechanical equipment. And I've overemphasized this is a really tiny home, but it's to try and get the point across there. And this is where we need to take a look at. If you look at R value and U value, if you take a look in this area here, we want to be somewhere in there for our energy use there. So when we take a look at how do you do that, where do you go, we have some tools out. Air leaks by wind and by mechanical equipment and by stack effect. And so a very tall building, which I'm showing here, creates a buoyancy effect depending on the height of the building and the temperature difference. So if you have a really hot climate and a really tall building, which we have lots here in Las Vegas, you're going to have a good chance you're going to have huge stack effects. That creates a high pressure at the top of the building, low pressure at the bottom of the building, in cold climates, and the reverse in hot climates. So we can control those different ways. You can see in this slide we're sort of showing air leaking out everywhere. And of course, if air leaks out, air has to come in. And that's why you have to condition it. So we're taking air from outside, heating it, cooling it, add moisture, subtracting moisture. So every time we use a cubic foot of that air, we got to bring another cubic foot in. And not only getting the heat going out and so on, but if we have a very leaky building, it's really hard for your mechanical equipment to work right. And the point of this is if you have the air coming in here, it's being distributed and so on as you go throughout the building. If these parts of the building leak like a sieve, it's going to have a lot of air leaked out those holes, and it's not going to go through your distribution system. There's one study, this was done on multifamily residential in the state of Washington, that showed when they had a distribution system heating a number of different units, the end unit, the last unit, got 10% of the air that they were supposed to get. And that it gets back. If you have a super airtight building, and if you seal all your ducts, then the air is going to get to where it needs to be when it needs to be. It'll be a lot more efficient there. In the old days, we used to heat or pressurize the corridors. And the idea is pump a lot of air in the corridors. That would go into the suites, and then that would go outside. And that would keep cooking orders or smoke or whatever it might be from coming in the building. We're able to push it to the outside. We realize today that's not a very smart way of doing things, and so our designs are changing there. When I talked about a stack effect, here's a representation where you have air leakage going out, air leakage coming in. Let's say this is a 6-story building. You can compartmentalize it, so you can see the difference between the pressure difference by simply sealing the floors. Now that should be done by the fire stopping. Every floor should be separated, but it's not being done right, so we get leakage. And this is more real. We have not as airtight as this, but not as bad as that, and that's a step forward. The other thing that air leakage does, when we think of hurricanes and high wind events and destruction, our past chairman has a house on the coast in Texas. He's been hit by 2 hurricanes directly on. He has not lost a shingle, whereas everything around him was devastated. And it's basic physics, because what happens if you have a leaky building, you have the inside being pressurized at the same time that the wind's trying to take the roof off. And so his house that's completely sealed, doesn't have this overpressurized. You still have the wind time to take the top off and blowing against one side, but your house is built, or your building's built to withstand that. It's not built to withstand this. And so we've seen, and even in Florida, where huge hurricanes come along, if you got an airtight building, it survives much better, getting back to the resiliency. Just to show air barriers again, these are GFRC panels, no insulation with insulation, and no air barrier in insulation. And you can see the temperature difference. So you have no air barrier, but you have insulation, compared with an air barrier with insulation or just an air barrier. Of course, this is the best way to go, but if you have lots of insulation in but no air barriers, the air goes through the insulation and you're reducing its efficiency. So, high performance building, we should be looking at 0.025 for U value. Fenestrations, this actually should be even lower, should be 0.6 or 0.5, and our building should be in the neighborhood of 0.05 cubic feet per square foot at a pressure difference of 1.57 pounds per square feet. That's where we need to go for a high performance building. Now, we have materials. We have a lot of good materials. We got good fenestrations and so on. But part of the problem we face is that when they're installed, it doesn't work. This is really important for air barriers because you can't see air barriers. So you don't, you can't see air leaks, so you don't know how good a job you did. And so we need to have quality assurance. We have to have proper installation. This is what we're trying to do in place. Now, this is a nice picture to see, but even if it's in an office building or something, we want to be comfortable. We don't want to be subject to outside pollutions and so on. And we got to think that buildings all work together. You can't just do one thing and walk away and expect everything to work. One thing impacts another thing, so we got to do everything as a whole system. This is interesting because it looks like a good picture, right? But just follow the water. So this has now that's all flat. So how do you move water from this level to the other level when it's all flat? And the point I'm trying to make here is you can draw it. If it's an architect, some of the details that I've seen, it's this type of thing. So you can draw it, but you can never build it. In some cases, you might be able to build it, but it'll never going to work. So bad designs gives you, or bad materials are going to give you a building that doesn't work. So we have to start out with the design side. I mean, what were they thinking? And there's lots of pictures out there on there. And this gets back to, and I can't believe it, I've had contractors, I guess they're more project managers, say to a contractor, I don't care what the plans say, you build it as you're told. And so a lot of these things happen, and somebody should find out where the adults are as we build buildings. Now, here's the point I'm trying to get to. And in case if you're in the audience here, this is a telephone. This is something we used a number of decades ago. And there was no buttons to push, although I've seen people try and push these buttons. There was a rotary dial. So today we look at is extremely primitive, and we look to, the phones that we have today, which are fantastic. The point I'm trying to make here is we used to build really good buildings. Some of these, I was over in Stockholm where I see buildings 100 years old, 150, 200 years old, sometimes even multi-hundred years old, but they worked. And now we're buildings different. Now this has nothing to do with buildings, but this is a flow chart for standards and conformity assessment bodies in the United States. Now if you can figure that out, I will buy you dinner. But this is real. This is what you have to go through. And some of our buildings are like that. They're becoming so complicated that it's really hard to figure them all out. We build beautiful buildings today out there, but in some cases we're not bringing the technology forward out there. And we got to start, as I mentioned earlier, we can't think of our buildings being there for the life of the mortgage, 20 years, 25 years. you've got to think of it at least in 100 years, if not longer. My own personal experience, I bought a used home. It was about 25 years old when I bought it. I've been there 23 years, and I want to sell it, and I want to sell it for more money than I bought it, and I'm sure the person that buys it from me is going to want it to last another 40, 50, 100 years. And we got to start thinking that way, because that will change how we build buildings. Old building, right? This is just down from my office building. By the way, my office building is 100 years old. Looks old, right? So we would expect no insulation in there, leaks like a sieve, cold, drafty, and so on. We tested one of these buildings, doing a whole building test as part of a procedure. It was super airtight. Because what you can't see is this is just the facade. It's turned into a community college. They wanted to do it. It was too costly to try and repair it. So they actually tore the building down, but they maintain facade. So looking at a building itself, you won't necessarily know whether it's airtight, well insulated, and so on. Again, my building's 100 years old. There is no air barrier as we think it today, but it's actually quite airtight. Meets actually today's standards on there. But how we build buildings and the people we used to build buildings and so have changed. We don't have the trades training that we used to have in Europe and was brought over to the United States. There's more and more shortcuts to it. There's not a lot of training courses going on for people in the construction industry. And so these are the types of things that we're seeing. If you want to know if your building sees air leakage, you can see right to the outside. You don't even have to bring a test equipment out. You know that it's not there. But we do a good job. This is actually a building in Las Vegas. There's a whole story behind this one. It's about 20 years old and it hasn't been finished yet for a whole bunch of reasons on there. And then these are the type of horror pictures. This is interesting. This is up in Minnesota. There is 5 houses that basically had moisture damage. If you saw the cladding on the house, you would not be able to tell there was a problem with those homes. But there was some testing times, moisture was found, and so they took all the cladding off. Notice how there's no reason to have rotting here. This is not a leak underneath the window or anything. And these 5 buildings, as I say, you would never be able to tell there's a problem. And the repair cost for these buildings was close to at least 150, and one of them was up to $250,000 damage. You want to know how old those buildings were? These are homes in northern Minnesota, less than 5 years old. So what if you bought a brand new house and within 5 years you're selling out over $100,000? Now this was not liquid water coming from the outside, not from the roof, not from the windows, not even from a penetration. That's where you would expect it. It was air leaking into the building from the inside, condensating and causing rot and mold and mildew and everything there. And other examples of buildings that are having problems out there. I put this in here because a lot of times we start off with something very simple. This is C equals A plus B plus D, and then we get it more and more complicated, and then this is what we feel like at the end. We just want to hang ourselves because it's too complicated. It doesn't have to be that way. If we have the proper technical assistance, the guidance, the guidelines, the standards, and so on, we can help. The other thing, you're going to get a copy of the presentation, so I'm going to go in here. But one of the problems we face too is we do all our testing of materials in steady state. So it's one atmosphere, we do one test, and it's so we can compare one material to another. As soon as we change the atmosphere, and what I mean by atmosphere is temperature and relative humidity, we can change the material properties of whatever we're dealing with there. And so a lot of times we focus on a single material. This is an air and water resistive barrier. I can give you all the stats. I can tell you what the water vapor transmission rate was, the air leakage rate on, the elongation, and so on. But a lot of those things are based on a set of temperatures. So for water shedding, this is your cladding systems and so on, whether it's your roofs or whether it's water resistant barriers or so on. We test the single material, but we got to keep in mind as we change things. So one of the test methods is called AAT-CC 127. It comes from the textile industry. This is determine how water resistive your jacket is. And so we use that, we have been using that, and it works good for materials like house wraps, very thin materials. But if you ever put it on a thick material, you're going to get a false positive. Because what the test is, it looks for drops of water going through the whole thing. So I can take a piece of drywall, which you would never use on the outside of the building without protection over it. I can pass that test because there's no water that comes through the other side. Now, the gypsum is mush, but there's no water, so I pass. So we got to think about those ways. So we have some other water resistive tests out there, but we also have to look at on air leakage on not just on the materials, but the whole assemblies. That's that same building. This is another building just down the street. This is a limestone cladding. These are metal strips. Metal strips is to keep the limestone cladding on the building because it's falling off. And most of this is caused by air leakage. Take a look at the name of the building. It's a police shop. It's now been demolished and so on because it wasn't worth saving. So when we think of airflow, a lot of times we talk about air exfiltration, building air going out of the building. Air can't go out of the building unless air comes in the building. So we got infiltration, got cavity ventilation. That's good. In fact, the Rain Screen Association over in the corner is really dealing with how do we use cavity ventilation to keep our buildings dry out there. But you can have wind washing, which is air coming in, going through your insulation and back out, but not actually coming into the building. You have the same thing coming from the inside, and then you have air looping. These are all bad. This is the only one that's good to your whole building that's out there. I'm going to go through these really quick because the point I'm giving across here is you had pipes going through here for the water system on there. They were freezing. They had to keep the temperature way higher. It cost them a whole lot of money. And the problem was air leakage at the top of the building. So pipes, sprinkler pipes were freezing at the bottom, but it was caused by air leakage at the top, which was allowing cold air to come in and freeze the pipes there. As they went through and they took a look at it, and we see this all the time, the connection between the wall air barrier and the roof air barrier. If you look at a lot of drawings, it's got an arrow and then it's got by others, because nobody wants to take responsibility for it. So if you ever want to start a contract and get instant business, call it by others, because you can show everybody you're already in the contract. So the simple thing is the air barrier material that's on the roof has to be connected to the air barrier in the wall. And that's what they did. This is a bit of a video that doesn't work, but they were showing a clinic that's just fluttering like crazy. So all they did is they went in and they put an air barrier block in there. They covered with thermal insulation for fire blocking and so on, and it solved it. As we go into checking thermal insulation, this is a thermal. You'd use a 12-inch by 12, or yeah, 12-inch by 12-inch piece. Put in there. You have a hot plate and a cold plate, and determines what we call the thermal insulation value on it. Keep in mind as you change the temperature. This is tested at 23 degrees centigrade, which is about 73 Fahrenheit. But if you change that temperature, you're going to change the insulation value. That's why the roofing industry has a big issue right now, because they say things like polyiso isn't performing. Well, polyiso wasn't tested at 200 degrees Fahrenheit on the roof. It was tested at 73, so you're going to get a different number. And if you use a cellular plastic and it's in the wintertime, the gas inside the cellular plastic condenses to a liquid, and again your insulation value goes down. Here's Water vapor transmission rates, and this is the most misunderstood control layer we have in our buildings. It's really simple. You either put a desiccant or water, so that would give you 0% relative humidity or 100%. You put whatever material you're testing. You put it in an oven that is at, again, 23 degrees centigrade, 73 degrees Fahrenheit, and 50% relative humidity. So if this was water, so you got it going from 100% to 0 or to 50%, so that would be 75% relative humidity. If this is a desiccant, then it's 50% to 0, so 25. So I ask, and if you go to the code, you test it according to desiccant. So how often do you think your wall or your roof or whatever it is ever going to be at 73 degrees Fahrenheit, 25% relative humidity? I'm going to suggest it's seconds or minutes, at the most hours per year. Now, what happens if you change those? This is actually a meter that we can test it at various temperatures out there, so we get more of them. And here's just an example of a material that is designed to let water vapor go through it. We have problems like house wraps and things like that on there. We use this, there's a product called Gore-Tex, and it's used a lot in jackets where if you're out there in the wintertime, you want the moisture that your body creates to get evaporated, but you don't want the wind, you don't want to feel cold. And so they allow a lot of water vapor to go through. Sounds good, let's put it on our buildings. Now, what you have to keep in mind is, again, going back. This is a study we did with all the water vapor transmission rates on the ABBA website. You can take a look at it. Here's the bottom three lines I want to take you out. These three lines mean the same material. Remember I said water method and desiccant method? This one here, and these are nanograms, these are not perms. 4.96 to 4%. Now a nanogram is a billionth of a gram. It's extremely low. So you know this material had tested whether water or desiccant is the same, absolutely the same. Took another material, it goes from 4.3 grams, and there's 57 grams to a perm. It goes over to 1810. 42,000% different. So if you're a design professional building owner and you go to the code and you say the code says I need desiccant, and you look up a material and it has 4 grams, that's 0.01 perms, and you design your building with that, it's going to be really, really low vapor permeance on it. And then we put it in our building and we go to just 75% relative humidity and 23 degrees Fahrenheit. We're now up to 1800. A lot of moisture is going to be coming in. And so we see this happening all the time out there. Solar radiation. A lot of times you can see my material should be covered within 6 months, 3 months, 30 days, whatever it is. It doesn't mean anything. I've worked with the manufacturers of the equipment that does the testing, and there's really no correlations between how many hours they put it under these lamps versus how many hours you have in the field. And it makes sense. If you're going to put something on the outside here in Las Vegas for a year, the amount of sunshine you're going to get here is going to be completely different in Seattle, Washington, where it's misty and rainy and so on. So what they do is they come up with roughly how many hours. So it helps you compare one material to the other material, but it has no relation to whether it should be left uncovered for 30 days, 60 days, 6 months, 1 year, whatever. Sound rating. All our sound ratings is done on impact resistance and so on. But you're hearing me by sound transferring through the air. So what I've seen in my history as we build more airtight buildings and we make them airtight on the inside too, first of all, on the outside, we hear very little noise from the outside. If your windows are nice and airtight, your building's nice and airtight, you don't hear the traffic, you don't hear the other things. If you're in a multifamily residential and we put air barriers, what we call interior air barriers, we seal one unit from another unit, You don't hear the person talking, you don't hear them on the telephone, you also don't smell what they're cooking, and so on and so forth. So we got to start looking at how sound is transferred, and let's seal those paths that we have out there. Most materials are required to be tested for flame spread, and then we also have an assembly test, NFPA 285, where we test a 2-foot wall and we see how fast it burns. Very important testing on there. And as soon as we change any material in that assembly, then we should redo the test. And it'll only cost you $50,000 or $60,000 to do the test. So every manufacturer wants to run out and do it on every material. And they don't do that. They get engineering judgments, but it's an important part of it. Here's what we do most of it on. We just measure how fast the fire goes down in comparison to red oak. So again, getting together this assemblies, the systems, things working together. Don't just look at one part. If you're looking at your building envelope, take a look at how you're controlling the liquid water. That's your cladding system. You're going to learn about a lot of that here. Then you have to go to your air control layer. Come and see us at the Abbott booth. Tomorrow we're going to have some installation instructions. Take a look at your thermal insulation, and then you take a look at your vapor barrier, vapor retarder, what you need. And you got to put them together so that they work. The other thing we have to do is we do a lot of testing in the laboratory, which is good, but we also have to go to assembly testing, and we have to do whole building testing. And again, as I mentioned, we don't know how good a job you did with an air barrier unless you do the whole building testing, because you can't see air leaks, so you're doing your best, but once you see the air leakage, then you know what you've done wrong and you can fix it. So I always used to say that if the only thing we worried about was the air leakage rate of the material, Jello or with peanut butter would pass. And I had nothing to back me up, but I actually got a lab to test peanut butter. Yeah, it did pretty good. So I was going to quit my job and I was going to become the next air barrier supplier. It was environmental friendly, it was growing probably within 100 miles of your building, you know, all these things, and I could retire, come down to Las Vegas. Well, then people pointed out there are a lot of people allergic to peanut butter and it attracts rodents and it cracks when it dries and so on. And so the whole point about that is that we got to look at a material in its entirety. So again, if you're looking for air barrier materials, we have what we call material specifications and what all the tests, elongation, compression, whatever's important for that material to do all that testing so you know it's going to perform in the field. Here's how we test air leakage. It's 39 inches by 39 inches. We create a pressure difference, we measure it. Here's your peanut butter test. The requirement is no greater than 0.02. So the test of this material, 0.002. So it's one tenth of what was allowed. And I always get asked what type. It was Kraft, it wasn't Skippy or anything. And it's smooth, it's not chunky, so I don't know how those would do. And we've got to take a look at it, how we do it in the whole building. This is just a typical wall section. We know heat flow, air flow, vapor flow, and rain penetration or liquid water are the loads. That's the most important part that we have to do in our building envelope out there. And what I'm trying to show here, this is dealing with air leakage, but applies to all our materials. So we can test the material and we get some good information. We have to move to an assembly test. So we have tests for wall assemblies and roof assemblies, the air leakage. But these two are all done in a laboratory. And again, until we go testing whole buildings, we don't know how good a job the installer did. The other thing that we don't realize is the pressure difference. So when we test in that assembly that I showed you there, we test these numbers here. So that is an 8-foot by 8-foot wall, and we put a pressure difference of 400, 600, and 1200 pascals against it. And at 800 pascals, as we're running the test, we put 800 positive, 800 negative, and so on. If it's a steel stud wall with dense glass on the outside, the middle of that wall will move back and forth about 3/4 of an inch. That's at 1200 pascals. Those pressures are good for 80% of the buildings that are 3 stories and less. So there's some buildings in the United States that's not enough pressure, and if you're over 3 stories, that may not be enough pressure. If you go to, let's say, Boston, high wind loads, you're about 5,500 pascals. At 5,500 pascals, unless you have special windows, the glass is going to go out of them and so on. And people just don't understand it. Now, we don't build, for the number of buildings we build in the United States, the percentage of buildings that are really, really tall is very small. And those are all engineered and so on. And one of the things that helps us is the fact that most of the air barrier materials go on a substrate already. So that substrate has already been designed by the wind engineer to withstand all the loads. So as long as that stuff stays with that substrate, we're okay. This is showing the testing. This was done just outside of Kansas City as a laboratory, and this is where we tested up. We didn't hit 55, we hit 4,000 pascals, and that's where the whole window went all to pieces. This is a building that we tested up in New York. I was asked to go on the project to watch it and so on, and I heard I'm going to Jamaica, so my hand went up, and then the plane landed in New York, and I ended up in Jamaica, New York. But it's a really interesting test. It's a 12-story building, 1 million square feet, whole block. Give you an idea, the louvers, a lot of times in buildings you have to seal the louvers from the outside. We didn't have to worry about that. We just climbed right inside to seal it. You can see the size of the ducts and things like that there. So we conducted the test over it, and the test was conducted because they had a lot of problems with the building. The architect says it's air leakage. You got to make your building airtight. It was owned by the government. They didn't want to spend the money, so this test was to show that's the thing to do. The other thing we test is for wind damage. Down in Florida, there's an area of codes where you have to test windows by shooting a 2x4 at them at a certain rate. I think it's 40 miles an hour or something like that. And the the glass can't give way. It can crack, but it can't give way. So it's kind of cool to watch this. Somebody was going to a presentation on this, and they're saying, well, the window doesn't go into pieces, protects you, and the guy's going, well, what about the wall beside it? And the answer is it would go through the wall. So contrary to what everybody tells you, stand by a window in a hurricane. No, don't do that. Water shedding. We got a lot of different, this actually not only sheds water, this is for flood surges. So if you have a patio window and you're in a flood zone and you get 2 or 3 feet of water on it, can that door, window, or whatever withstand it? And this is a testing facility. They have a great big reservoir of water. They put the door or whatever it's going to be, and all that water comes down really fast. Good testing. This can be anywhere from 8 feet by 8 feet. This is, I think, 30 feet by 30 feet, where they'll take a whole wall section and they'll test it. A lot of times this is done before they build a building. If they're going to build a 5, 10, 15, 20-story building, they want to know whether things work before they actually build them. So they will do all the testing in the laboratory to make sure that they're getting everything watertight and airtight. So, sorry, this is kind of hard to see, but it's really just showing the cladding. The airspace you typically have behind the cladding. Red is the air and water resistant barrier. Then you have the thermal insulation, the exterior sheeting, your backup wall, and your interior sheeting. So all of those things have to be put together with the right amount of control layers in them to make sure that they work. So this is just a picture and a schematic of how we test roofs. So all roofs have to be tested for wind uplift, because as wind goes over the building, it wants to suck the roof off. So it's actually really simple to then just test the air leakage at the same time, because they know as they push air in here to show how the roof is going to be lifted off, they just have to measure how much more air they got to keep putting in there to maintain the pressure. So it's a relatively easy thing to measure air leakage while you're measuring roof uplift there. You can see the different test methods with a number of fasteners, all sort of part of that testing, what keeps the wind down there. So when we take a look at fasteners, though, one of the things that they're starting to look at is what we call thermal bridging, is when we're putting pieces of metal through insulation, how much does that reduce the effectiveness of the insulation? And you can see 20 to 30%, which reduces the total building envelope 2 to 3%. That's a big deal. The answer to that is really simple. As you fasten the first layer down, you glue the second layer down. So you're covering your fasteners, and that stops the thermal bridging that's out there. There's an energy saving calculator. It's on our website. We also added a moisture transport. And energy saving, people look at it and they might save $2,000, they might save $30,000 a year, and they sort of yawn and they go home. But what we do get them to take a look at is the amount of moisture that air is carrying. So we started out with 4 units, high-rise, hospitals, large hotels, secondary schools. We've added to it. You simply pick a city that's closest to you, because there's 50 cities identified, and they represent all the climate zones we have. United States, you pick where you're going to do it. You pick the type of building, a prototype. You can put in the air leakage. You can use the default. You put your own in, and you can calculate not only how much air leakage that you have, but how much moisture is going through your wall. It's going to be hard for you to see it, but this is a secondary school. It is 211,000 square feet, so it's a fairly big building. 734,385.29 gallons of water goes through the walls and the roof of that building per year. Okay, even if you calculate that back to the day, that's a lot of water. Now you can reduce it down, and it only brought it, because of the difference in air leakage, brought it down to 231,000 gallons of water, but that's still about a 70% reduction out there. So the most important place to ever put an air barrier is Houston, Texas, Miami, Florida, anywhere it's hot and humid, but we really need it in every building right across the United States. But go through, do some playing in it, and so on. So the point I started out with is we've got to start really addressing high performance building. It's a necessary thing that we need to do for a whole bunch of reasons. I really believe various associations should be part of it. Thank you for coming today to Metalcom. Thank you for coming to my presentation. And I really think as we work together, we're going to develop the technical information that we need to go back to builders and so on, code officials, and that we can actually meet some of the goals that we have in the future. Any questions?
We used a blower door test, all building test on a small tank building. I was impressed. I mean, we were having trouble with it, and it found the problem. The question is there a limitation to the size of that test, or do we have to go to something more sophisticated? I'd like to do it more often.
So the question was, if I got it right, is do you have to go to more sophisticated equipment as buildings get bigger?
Yeah.
No. You just have to use more of them. So that job I showed you in Jamaica, New York, we had 33 fans there. Okay, and we put a lot of them in the loading docks and so on and so forth. So 2 things are happening is we are building our buildings tighter. So what we needed 2, 3, 4 blower doors, now we only need 1. There's no building that's too big. It's just the amount of fans that we need to do it.
Does that increase the cost? I mean, the test was, I think, in the range of $10,000 or $15,000, right? And that was fine because we had a problem, and it was time to solve the problem, so we needed to do it. But what I want to do is just have the test worked into a specification and just make them do it. And if that cost gets too much more than $15,000 or $20,000, I got an owner that's going to look at me and say, hey, I'm designing you to do this building right the first damn time. Why would I pay another $100,000 to have it tested?
And that's a question that's asked by a lot of people, like, why do I have to pay to test the building because I'm paying to have it built properly? But again, going back, we're doing buildings a lot better now. So what might have cost $50,000 10 years ago might cost you $5,000 or $6,000 today. So the more we can make our building tighter, the less work that we have to do to test that building, less number of fans we do. But it's not exponential. If you tested a 10,000 square foot building, and you test a 50,000 square foot building, it's not 5 times. It might be double the cost. It might go from 5,000 to 10,000. The other thing is we're learning how to do the blower doors much more quickly now. And so what used to be days and days, short period of time. We deliver training on blower door testing in Seattle, Washington right now, and there is one of the manufacturers left the course to go to a job site. It was a 6-story building. It was about 25,000 square feet. People were in the building while it was being tested. The test took 2 hours. But that company had everything set up. Their truck was set up so it was take things out. The guy that went there offered to help them load the truck, and they said no way, because they had everything down pat. So our blower door testers are learning how to do it more efficient on it and so on. So the average cost of, I would say, if you're looking at 3 stories and less, you should be looking at around $5,000, $7,000.
Yeah, ours was $15,000, and that's fine. $5,000 to $15,000, anybody I think would pay for that. But I'm from Nebraska, and we had trouble even finding somebody who could do it. We had to go to Kansas City.
So that's the second part to your question. The question I get as I deal with codes is, how do we know the guy's qualified? How do we know we have enough people? So our training and certification program answers, are you qualified or not? We have now certified blower door technicians, certified in accordance with ISO 17024, and we're having more and more of them. We're delivering them in Penn State, Syracuse University. We're going to be into Texas and California. So we're going to have more and more people out there to be able to do that. The other thing is we are updating our specs. We have project specifications that we use the building owner or the architect download and put into your contract documents, and that is going to include whole building testing as mandatory. So if they're going to use our spec, they actually have to take that out. And we find design professionals don't do it. They will just take it and put it in. So I think you will see more and more codes are making it mandatory, and more projects are becoming mandatory blower door testing before it even goes out for bidding. So it helps address that to a certain extent.
Sounds good. We had more problems in the building that cost way more than the test did.
Oh yeah.
We've done the test first. It saved everybody a lot of headache.
That goes for doing mock-ups and everything in the whole building. But it's always hard to spend the money if you don't think you have to.
Does anyone else have any questions? All right, well with that, we're going to say thanks so much, Laverne, for a really informative presentation. We have a